Hey, we're really glad to have you here. I know you guys are busy. Nathan, can you hear me okay?
I can hear you a little bit, not very well.
Oh, okay, I'm sorry. We're really glad to have you here. I told the students a little bit about the kind of work you do. If you could give them and the teachers, the educators, a little bit of what you do, if you can give them a short introduction about yourself, and then jump right into the big picture, and then your area of expertise and what you're going to be working on.
Okay.
Thanks, Nathan.
So I'm what we call a mission designer. I design trajectories, and so for the ARM mission, I'm leading a team of people doing the trajectory design for the asteroid redirection. So I'm going to talk in detail about that, and I'm going to start out by giving you an overview of the mission and the sequence of events that make up the mission, and a little bit about the asteroids. So one thing with the ARM mission, asteroid redirection mission, what it's going to do is it's going to look for a small, like 7-meter asteroid, and we're going to look for it using telescopes on Earth and a survey of the night sky. And as we detect small asteroids, we're then going to use assets around the world to characterize them, and that includes infrared telescopes that can tell us something about the spectral type of the asteroid, and radar, such as, I don't know if you've seen pictures of the giant radar dish near Arecibo that was in the movie Contact, but also large dish at Goldstone in the California desert. And we're going to light them up with radar to determine the size of the asteroids and where they are. And then for each asteroid, we're going to look through and design trajectories and see if we can bring back enough mass to match the mass estimate from the asteroid characterization. And so the point of the ARM mission is there's a lot of different reasons for doing it, but the fundamental reason is a technology demonstration mission. So ARM is going to use a 40 kilowatt SEP system. There'll be 50 kilowatt arrays on the spacecraft that will drive an electric propulsion system. And Dave Manzella is going to talk a little bit more about the details of that system. But that is a 4 times the size of the Dawn system. And Dawn is a spacecraft that's on its way to the asteroid Ceres, just flew by the asteroid Vesta. Sorry. Ceres is now a dwarf planet. It's a spherical body. It's a small planet, not really a potato in space. Anyway, as we increase the power level of SEP systems, they are effective for moving larger and larger masses. And we want to get to the point where we can use SEP systems to move masses that would be needed for human deep space missions. And the asteroid retrieval mission, we're moving an asteroid of up to 1,000 metric tons, more commonly 500 metric tons, and this gives us the ability to develop technology that can be used for later human spaceflight missions. So let me start out with 2 YouTube videos. The first one is of it shows the asteroid population, and it starts from 1980 and shows as asteroids are detected. And the video is narrated, so I will shut up and let you listen to the narration. But I'm going to tell you, look for 2 things. Look as the rate of discovery changes. As we approach the present day, we're discovering a lot more asteroids because we have dedicated assets to search for asteroids, including in-space assets. You'll notice when asteroids are detected that are opposite the direction of the sun, so they're 9 degrees off, those are detected from the ground using visible. And then you also notice ones detected in other directions eventually, and those are from spacecrafts using infrared. But let's run the video. And oh yeah, also look for the red ones. The red ones cross Earth's orbit, so they're potentially hazardous, but they're also potentially ARM retrieval targets if they're small enough.
Nathan, you can see our screen, right?
Yes.
Okay, I'll start with this one.
That one there, yes.
Hello, this is Scott Manley, and I'd like to talk you through this video I created showing the rate of discovery of asteroids for the last 30 years or so, starting in 1980. Now what you see here is a top-down view of the inner solar system with 4 planets in the middle, and on the edges you can see Jupiter. What you also see is a large number of
I'm gonna
green,
stop for a second.
yellow, and...
Nathan, I can't get this to go big.
Just use the link instead.
Yeah, where is the link? Is this the one? Let's try that one. That's the one we're gonna watch later.
There you go.
No, I think that's the wrong one. Hold on. No, that's not that one.
There is a link above the one you put.
Let's try this one.
I'm Thomas Roberts, and the Supreme Court is about to return monumental decisions on DOMA and Prop 8. Join me.
Hello, this is Scott Manley, and I'd like to talk you through this video I created showing the rate of discovery of asteroids for the last 30 years or so, starting in 1980. Now what you see here is a top-down view of the inner solar system with 4 planets in the middle, and on the edges you can see Jupiter. What you also see is a large number of green, yellow, and red spots denoting the position of asteroids. The colouring is primarily to indicate how close they can come to the Earth. Green are main belt asteroids, yellow cross the orbit of Mars, and red cross the orbit of Earth. Also, as asteroids are discovered, we flash them white to make them more obvious. Now, if you look in the bottom left, there are 2 numbers. The first is the year, and the second is the number of asteroids known on that date. Now, you can see this number grows as more objects were discovered by astronomers. In addition, the highlighting of the discovery location lets you see patterns in the discovery process. The most obvious pattern is that most objects are being discovered opposite to the direction of the sun. And this of course makes total sense, since you're going to be looking for these things in nighttime skies. Sometimes you see big flashing discoveries lined up with another planet. Scientists were perhaps looking for new moons around these planets, but found asteroids as well.
Sorry, I think there is another one that's...
In the 1980s, most imaging is being done with photographic plates, but by the time the mid-90s roll around, electronic imaging becomes the standard. This gives a significant increase to the discovery rates, since the turnaround time for image processing and analysis gets much faster. When you're trying to discover objects moving across the night sky, it's very important that you follow up on the observations before the object moves too far and is lost. Now, by the late 90s, a number of dedicated asteroid discovery programs are in full flow. These combine electronic imaging with automated image processing and follow-up. Hundreds of new objects are being discovered every day, and new patterns of discovery become evident. If you watch, you can see the discovery rate pulsing roughly twice a second. This corresponds to the lunar cycle. During a full moon, it is harder to discover faint objects since the moonlight makes the background sky brighter. There's also a sparse dead spot around the 5 o'clock position. Apparently this corresponds to the cloudy season in Arizona, where a number of these automated surveys are based. Now by mid-2000 we're starting to see hundreds of thousands of known objects, and it's getting very crowded in the inner solar system. But you need to appreciate the distances here are huge. 1 pixel at the highest resolution is still 500,000 kilometers. So all those objects apparently buzzing the Earth are still a long way out. And now for a few seconds you're going to see the discovery pattern of WISE, the Wide Field Infrared Survey Explorer. That was a space telescope designed to image the entire sky in infrared. And so we're almost up to the present day, and we have over 500,000 asteroids in our database. I'm Scott Manley, thanks for...
So that's the hunting ground. Most of those asteroids are larger than the ARM targets. The technology only recently is to the point where we're detecting things as small as 6 or 7 meters. These small asteroids, what happens is when they hit Earth, you get a fireball in the sky. If they're a little bit larger, you'll get things like Chelyabinsk, where you get a large nuclear size explosion up in the upper atmosphere. And a little bit larger than that, then they become what we call city killers, which basically can wipe out a city. So what we're looking at ARM are the small ones that are just basically fireballs if they hit the night sky. That way, we can develop the technology safely without doing a riskier asteroid. They have less inertia when they spin, and so they're easier to detumble so that we can capture them and redirect them. So if you can pull up the other video, I'll talk through it, so mute it. Also, I mean, some of you may like the dramatic music, but it kind of annoys me. It's hard to talk with it. So. So a lot of you may have seen this video. It was what NASA released when they announced the Asteroid initiative.
Do you see it, Nathan?
Yes, I can see it.
Okay.
So here's the object for retrieval. It's about a 7-meter object, and probably about 500 tons, though. They can be much heavier if they're depending what they're made out of. So it's an electric propulsion spacecraft, and in the front you'll see that white thing is a cover over the inflatable capture mechanism. So it uses electric propulsion to reach the asteroid, and as it approaches the asteroid, the cover is deployed. The cover is to protect the inflatable from micrometeoroids, and then the inflatable structure is inflated. By keeping the time that it's inflated small, we reduce the probability of a micrometeorite hit. There's a lower cone section, and then the larger kind of envelope that will be used to surround the asteroid. So the 7 meters is the average diameter of the asteroid. There's a 2-to-1 aspect ratio, so it could be up to 14 meters in diameter. Now, the ARM spacecraft will then match rotation with the asteroid to approach it as close along its spin axis as it can. It could be a non-principal axis rotator, which there'd still be a nodding motion as it approaches. And then the bag quickly deflates to get contact with the asteroid as quickly as possible. And as it cinches up with cables like a cinch sack trash bag on the outer edge to get a tight connection with the asteroid. And then we use RCS thrusters, hydrogen thrusters, to despin the asteroid. And after it's despun, we cinch it up tight to the spacecraft. Now, one reason why we use a bag is we don't really know in advance a lot of details about this object, and many of these small objects are rubble piles, or even potentially something like a space dust bunny, very dusty material. And so by cinching up tightly, we can deal with those types in addition to large monolithic rock or metallic structures. So after it is placed in orbit around the moon, the astronauts will launch. And
it locked up here.
Can you still hear me?
Yeah, we hear you. It just the video froze.
Okay.
It's loading.
Here it goes.
So the astronauts will launch on an SLS and an Orion with what was pretty much already a scheduled planned test flight, a cislunar test flight. And the asteroid will then be in cislunar space in a distant retrograde orbit that I'll talk about in a minute. And they will rendezvous with the asteroid and attach their spacecraft to the asteroid retrieval spacecraft. So there is an attachment point at the base of the spacecraft that allows the basically the asteroid, the spacecraft, and the Orion all to be along the same axis. And the whole asteroid retrieval vehicle has to be pacified at this point for crew safety. So as they once they dock, there's you can see this there they've docked. You'll see a white boom The boom is used then to traverse from the Orion to the ARV vehicle, or sorry, the ARM vehicle is called ARV, Asteroid Redirection Vehicle, the spacecraft itself. Oh, frozen up here, okay. The Orion would carry 2 crew, and both of them would be used. Both of them would be used on the EVA, and then they can collect samples of the asteroid and perform other experiments on the bulk composition of the body. So even though we will be performing science on the body, this is not primarily a science mission. This is a technology demonstration mission where we would demonstrate the technology for the high-power electrical propulsion as well as technologies associated with crew operation around asteroids and methods for crew sample collection. In addition, this is a large mass that we will then have in an accessible place where we can visit multiple times. And so that makes it a very good place to start testing in situ resource utilization to see whether we can, what useful resources we can extract from the asteroids. Depending on the type of asteroid, we may be able to get water for propellant, or we may be able to get material that's useful for radiation shielding. I think that's pretty much the end of the video shows them re-entering near San Clemente Island by San Diego. Okay, that's the end of the video. All right, so let me try screen sharing on my end. Can you see my title slide?
Yeah.
Okay. So this is a hard problem, and it took a lot of people to figure out how to bring this asteroid back so that we could place an orbit around the moon. Now, although we're choosing an asteroid so that it would, if it entered Earth accidentally, if we screwed up, it would just be a nice light show. However, we don't want to lose this asteroid. We're going to a lot of trouble for it, and we would like to keep it. And also, we'd like to develop technology and methodology so that we can eventually start bringing back larger asteroids. So along the way, we're trying to design trajectories such that at any point, if we lose control of the spacecraft, the asteroid is in a safe state. And also, the final storage orbit around the moon, which is shown in this title graphic, is something that we hope to be able to have stability for an indefinite period of time. So maybe if society collapses and rises again, the next mission to the moon will then be puzzled to why there's this big asteroid in a bag with an American flag on the side of it. Now, here's a mission timeline. So with mission design, fundamentally at the beginning, it is a timeline. It is like planning your vacation to Europe. You have a limited amount of funds, you have a limited amount of time, and a limited transportation ability. And so you have to go through and pick your itinerary and pick the highlights you want to see, and also be prepared for things to go wrong. And so that's the basic idea with mission design initially. So here's the timeline for the ARM mission. So right now we're looking at 2 different launch vehicle options. One uses the Atlas V, which is an existing rocket, and it requires a low-thrust spiral at Earth. to get enough mass to have enough propellant to redirect the asteroid. And so the low thrust spiral loops around Earth multiple times and then uses a lunar gravity assist to escape and insert upon the trajectory to the asteroid. For a heavy launch vehicle, such as the Delta IV Heavy SLS or Falcon Heavy, with the Delta IV Heavy being the existing heavy launch vehicle, and the Falcon Heavy being SpaceX's vehicle, which would, once it's developed, be more capable than the Delta IV Heavy, and then the SLS being the NASA vehicle, which would be even more capable than the Falcon Heavy once it's developed. With those vehicles, it's possible to directly launch the armed spacecraft directly to the moon for a lunar escape, or even directly to the asteroid. And this saves time because the low thrust spiral can, take a year and a half or so, and this allows us to spend more time redirecting the asteroid, which makes the redirection more efficient. And then once the trajectory around the Earth, we do a lunar flyby to escape if needed, and then a low thrust trajectory to the asteroid. There we spend 60 days characterizing that asteroid, getting a detailed surface mapping and a detailed estimate of the spin state. And then we approach up and cinch the bag around it as in the video. And then after we have the asteroid tied up against the spacecraft, we also characterize its mass in detail and prepare for the trip home. So step 4 is a low thrust trajectory from the asteroid to the Earth-Moon system. Now what we're doing is we're picking an asteroid that naturally comes by the Earth-Moon system anyway, and on its natural close approach, we're going to use the low thrust on the ARM spacecraft to nudge it so that it flies by at a different point and its aim point is close to the moon. And that allows step 5, a lunar flyby that captures the asteroid into Earth orbit. Now this orbit that's going to capture into is a loose orbit in the Earth-Moon system. This actually happens sometimes to asteroids. They naturally come close to the Earth and the moon pulls them in, and they end up being in orbit around the Earth for a few years before being thrown out again. So this unstable orbit we're going to enter, we're then going to do a little bit of thrusting and use a second lunar flyby to pull it into a storage orbit at the moon. And then we finally use some thrusting to trim that orbit so that it is long-term stable. And once the asteroid is in the storage orbit, the crew can launch in the MPCV Orion and rendezvous with the asteroid and then perform that part of the mission. On the next slide, I'm going to talk about picking asteroids. So in order to use a lunar gravity assist, we need a V-infinity with respect to the Earth of about 2 kilometers a second or less. So what the V-infinity is if you calculate an asteroid's kinetic and potential energy with respect to the Earth and convert it all into kinetic energy, the velocity you get from 1/2 mv squared is the V-infinity. And so when that energy, the V-infinity is then a measure of that energy. And so when it's slow enough, the moon can capture them when it's below about 2. And below here I have a couple example targets that all are dynamically capable to be captured. But the problem is not how well we have characterized the asteroids and how much we are able to estimate the mass. So this current mass return capability is, out of all the trajectory designs we've done for those asteroids, our best performance for asteroid mass. So if you take 2008 HU4, it could be up to 1,000 tons, and we could still return it. And that's because it has a very good approach geometry and a very low V-infinity. And it would return in April 2026. But we know very little about this asteroid. However, in the last column, you see that there's a close Earth flyby in April 2016. And so at that Earth flyby, we can observe the asteroid and determine its spectral type and use radar to measure its size. And then we can determine if it is 1,000 tons. And if it is 1,000 tons, then it becomes a viable target. If we look up on the top, 2013 EC20 is one that was actually discovered this March. And for that, we have a maximum return capability of 120 tons. We actually think the asteroid is probably less than 100 tons based on characterization during that encounter in March, and we confirmed that again in August 2013. However, even though here I have it in this slide, the asteroid diameter is 3 to 6 meters. After I made this slide, they were able to back out the Arecibo data that the asteroid is less than 4 meters. So the problem with this asteroid is it's possibly too small. Pardon me. So it's not going to be much larger than the ARM spacecraft. And so we'd like to go for something better. So even though this is a viable target, we'd like to find something bigger. 2009 BD is another asteroid, and it returns in 2023 naturally. And we could return up to 590 tons if everything was perfect in the trajectory. Currently, we think its mass is probably below about 325 tons. I have on the slide a Spitzer opportunity in June 2013, but we're actually going to use one in October. And so the Spitzer Space Telescope is an infrared telescope trailing the Earth. And 2009 BD naturally it's near the Spitzer right now. And what we're going to do is use Spitzer to measure its spectral type, which will then give us an estimate on its mass. And so if the mass is well characterized, it is also a viable return target. And similarly with 2011 MD, that has flies near Spitzer in January. And so that's another one. If we characterize the mass below this given, we could also return this in 2024. So I'll show you in a bit, there's this website, ssd.jpl.nasa.gov, and you can look at these asteroids and you can see their natural return dates. And so the methodology is we've gone through all existing asteroids and find ones where there's about 30 of them that are dynamically such that we could return them. And these are the 4 that have good chance of being characterized. For newly discovered asteroids, what we can do is the asteroids are around the Earth for a couple of weeks. And so as they're discovered, we check them to see if we can return them their trajectory. And if we find when we can return the trajectory, then we use global assets, infrared telescopes, and radar to characterize them so that we don't have to wait for a future apparition. And that's what was done with 2013 EC20, and we'll do this with new asteroids as they come up. With current assets, we expect to find about 2 a year that could be characterized. However, we're looking to upgrade the observation capabilities to double that number to about 4 a year. On the next slide here, I have some more information about 2009 BD. I'm not going to go too much into this. Let me just give you a rough overview. So for the trajectory analysis that we did, we assumed a 400-ton mass for the asteroid. And this mass appears to be more than what we are currently calculating the asteroid mass to be based upon an area to mass ratio. So 2009 BD has been near the Earth in 2009 and again in 2011. And during those times, they were able to take astrometry, trouble pronouncing that word, sorry, astrometry of the asteroid. And that's basically taking images of the asteroid against the star background. And if you have a good star catalog that says where the stars are, you can then use the stellar background to calculate an angle from where you're observing to the asteroid. And as you take images multiple days as the asteroid moves, that gives you enough to reconstruct the orbit. And if you can reconstruct the orbit well enough, you can then measure non-gravitational forces on the asteroid, such as solar pressure. And gravity goes with mass. The non-gravitational forces depend on other things, such as the area of reflected sunlight. And by combining those, you can get an estimate of the area to mass ratio. And so now, if we assume in this table, if we assume an albedo range, so that's the percentage of visible light reflected. So something, the really high around 40% would be like a metallic asteroid. Above about 10% would be an S-type or stony asteroid, and below 10% would be a carbonaceous asteroid that would be dark. And so depending upon those albedo ranges, you get a size range of the asteroid. And you also can assume a bulk density, and combined with the area to mass gives you a mass ratio. And the allowable bulk densities are constrained by the area to mass, what we know is 2009 BD is a very light object. A bulk density of 1 gram per cc is water, and most asteroids are I think about twice this density. So this is kind of the uncertainty game we're playing right now with 2009 BD. What Spitzer's going to tell us is it's going to tell us an albedo range, and that will then constrain down these numbers, so that we'll then get, instead of a range that on the low end is 25 tons and the upper end is 4 or 5 tons, so that's I guess like an uncertainty of about 20 times. So we'll probably get a mass uncertainty of about 4 or 5, factor 4 or 5, which will then be much easier to design a retrieval system to. But based on what we know right now, assuming a mass of 400 tons, this appears to be a conservative approach to look at what we can do with the flight system to retrieve this asteroid. On the next slide, here we've done multiple low thrust trajectories, assuming different launch vehicles, such as the Atlas V in blue, the Falcon Heavy in black, and the SLS in red. And you see the retrieval capability for the SLS and Falcon Heavy are well above 400 tons for launches well into mid-2018 and actually beyond. The Atlas V, however, the mass drops off fairly quickly, and this is because you need to build a year and a half onto the front of the trajectory for the low thrust spiral. And so by the time you escape, you've kind of lost the best time to leave for the asteroid, and you're dropping off performance very quickly. And the time to leave for the asteroid, it's basically the sooner the better for most asteroids, because you have the time between once you get the asteroid in the bag to its natural close return. And the longer you have, the more time you have to thrust. And so the more efficient you can be with thrusting to redirect the asteroid. Again, let me continue on with the storage orbit. So when we retrieve the asteroid, we have to put it in an orbit that is stable. So we want to keep this asteroid we spent all this trouble getting, and accessible by the NPCV. And we also would like it to require minimal delta V for both the NPCV to reach and for the asteroid return vehicle to enter. And the one orbit we found so far that meets all these requirements is a lunar distant retrograde orbit. We have other ones that we think might work, but we currently need to do more study to see if they do meet all these criteria. DROs are very stable. We've established they're stable in the order of hundreds of years. So we expect them to be stable for longer, but we have to do the analysis to show how long they are stable. Once you get integrating beyond 100 years is a tricky thing. I don't know if any of you have a orbits or planetary science background, but you get numerical errors building up, and it's you can't just blindly trust the integrators. So we can enter this orbit for the ARV between 10 and 60 meters per second using long flight times, about a year and a half flight times. And also the NPCV can reach these. Showing in the lower right is an example trajectory for the Orion to reach the asteroid. And so it starts on the magenta line, does a lunar gravity assist and a burn, and then a rendezvous with the asteroid. In this case, it stays at the asteroid for, I think, about 6 days before doing a departure and another lunar gravity assist to return. We're timing this distant retrograde orbit to have a period of about 14 days, which is half of a month, half of a real month, a lunar period. And what this timing lets us do is it lets basically the geometry to repeat on a monthly basis, so you have good crew opportunities monthly to reach these targets. On the next slide here, I have some discussion of some other storage options to consider. So the Lagrange points, this is what a lot of people talk about for the asteroid retrieval. And what's nice is they are easy for the NPCV to reach, and they have a monthly recurring geometry. However, they're very unstable. And so that means if you put your asteroid there, your spacecraft has to keep working. It has to do small maneuvers continuously to stay in this vicinity. So if you lose control of your spacecraft, it's going to drift around the Earth-Moon system. It's not going to hit the Earth, but it's going to be drifting around, and over hundreds of years, we'll probably do lunar, maybe not hundreds of years, maybe like over a period of tens of years, it'll do a lunar flyby that will change its orbit, and it could eventually hit the Earth or escape the system. In addition to that instability, the instability requires about 10 meters per second a year to keep it at the Lagrange points. So from a delta V point of view, if you can find a way to enter a DRO for 10 meters per second, then that's going to be about the same as keeping it at the Lagrange points for a year. So it can even win on the delta V side. Now the Earth-Moon L4, L5 orbits, some orbits maybe in this region may be stable. There's a lot of disagreement in the literature about whether things can be long-term stable here, whether the sun or other planets kick things out. But that disagreement aside, it's very difficult for the NPCB to reach the L4, L5 Lagrange points, which pretty much rules them out. Other ideas are these lunar weakly captured orbits. And so these are elliptical orbits around the moon that are in a transition from a high lunar orbit that's kind of like a two-body problem orbit around the moon to three-body type orbits. And they're a new orbit class. They're poorly understood, so we don't really know what's possible with them. But they're exciting because they potentially could be as good as the DROs and could be easier for the MPCV to reach because they would have a low periloom by the moon where you can do an efficient maneuver to reach them. But they're a new thing and require more study. Another interesting idea is intermittent capture. So there are asteroids that naturally enter the Earth-Moon system and stay around the Earth for a couple of years before being thrown out. You potentially could design this behavior once you're controlling the asteroid so that when it's thrown out, it then enters a heliocentric orbit such that it will come back to the Earth a year later. And these potentially could be extremely low delta V and could allow even larger asteroids to be captured. And then another idea is an orbiting around the Earth with multiple lunar gravity assists, basically to keep correcting the orbit so that it stays in the Earth-Moon vicinity. This one is probably unstable, but there may be stable solutions there. But what's exciting about it is it could be extremely easy for the MPCV to reach. It could be easier to reach than direct trajectories to lunar orbit. So I'm going to continue on with the fire hose, and I will hopefully see how good I do in Q&A. But let me go on with the mission phases. So these are mission phases that are just used to kind of explain what's going on. These labels, they're nothing official, they're just useful for us to talk about it. So you have a launch and spiral trajectory phase. So if you have an Atlas V, you have a spiral trajectory. If you have another rocket, you just have a launch phase or a launch and then lunar flyby phase. And then what we can simply call a go-to leg that goes from the Earth to the asteroid. And this, we have the engine pushing us pretty much all out. We're trying to get there as soon as we can because we don't have a big asteroid on our back, and we want the time to bring the asteroid back. When we have a lot of mass to push, we want to maximize the time. Then we have the asteroid capture. So there we have 60 days at the asteroid for asteroid capture operations. And then once we have the asteroid all cinched up tight to the spacecraft and we can start nudging it, that's the fetch leg. And the fetch leg is going to retarget the asteroid's flyby to a lunar gravity assist that will capture it. And then the end game is after we have that lunar flyby, we're now in the Earth-Moon system in a chaotic, unstable orbit. And we're going to try to get to a second lunar gravity assist that will put us into the storage orbit. And this is a transition from the interplanetary to the storage orbit. And then LASSO. So the LASSO leg is named after inspired by George Bailey and It's a Wonderful Life, where he said he would last on the moon for his girlfriend. It's also an acronym being NASA, so it's you can say it's a Lunar Asteroid Safe Storage Orbit, or Lunar Astronaut Safe Storage Orbit, or Lunar Astronaut Stable Storage Orbit. Again, what the acronym stands for is less important than it's a lasso in a reference to lasso on the moon. Can't see you all, so I don't know if my jokes are lame or not. All right. So here's an example trajectory of 2009 BD. And so this has 8.7 kilometers a second at delta V, you'll see in the upper right. This is not something to try in chemical propulsion, especially because in addition to being high delta V, if you look from this Earth return to storage orbit, the delta V's get little because an asteroid is freaking huge. And so you can play with rocket equation and see how hard it is to do 150 meters per second with 500 tons, but you will see it is very hard. So on this trajectory, we spend about 4.6 kilometers a second with the spiral trajectory to the moon. With the larger launch vehicles, we can skip that part. So we can skip that delta V and we can skip that 1.5 years of flight time. We actually could spiral with the heavy launch vehicles because that 4.6 kilometers a second on SEP is more efficient than the delta V that the upper stage of the rocket would do. But the main problem is that 1.5 years of flight time. Then after we've escaped and gotten our way to the asteroid, we're going to try to get the asteroid in 2 years. And that takes 3.9 kilometers a second. You could get to an asteroid easier, but that's only in certain years. So what we're doing is we are trying to do a quick trajectory in a bad year, and that's why we need a lot of delta V to get there. And we're pretty much thrusting all out as much as we can to get the asteroid as quickly as we can. And then once we get to the asteroid, then we're going to do, in this case, for this asteroid, 150 meters per second over 3 years. So we're going to kind of take it leisurely and thrust at the right time and nudge it ever so slightly so that we get that lunar flyby. And then once we're in the Earth-Moon system, then in this design we have 60 meters per second in 1.5 years. Though these designs vary, and to be honest, we're still learning how to do this in-game analysis. And we can get that delta V in some cases all the way down to 10 meters per second and really save stuff there. All right, so I guess I got a picture slide to tell you a little bit about it. The red is thrusting and the blue is coasting. And we could thrust all the time, but what you want to do is by coasting, you let your orbit get eccentric, so that when you finally get to the moon, if you have an eccentric orbit, you're going to have a little bit more energy with respect to the moon, a little bit higher lunar V infinity, which means the moon can then kick you out of the system with more energy. So that coasting is there to keep the orbit a little bit elliptical, so that when we get to the moon, it can kick us out better. And then the black dots there are when we have eclipses. So as we're spiraling, there are times when the Earth will block the sun and our solar rays won't work. And we have to run on batteries. On slide 10 here, I'm going to show you the interplanetary trajectory. So here we have red is thrusting and green is coasting. And we're coming in below the Earth's orbit because we're trying to get there quickly. The Earth is, 1 year period. The asteroid is really close to a 1 year period. So if we want to beat them, we have to get down low so our period speeds up. Which is good from an orbit's point of view. It's bad because the sun is hot, and the closer you get to Venus, the hotter it is, which means that we need a sun shield to keep the spacecraft the right temperature. When we drop down, we do the thrusting in the right place, and we get to the asteroid in April 2020 in this design. And then 60 days later, we leave. And here, it's kind of hard to see this. In animation, I'm going to show you'll see it a little bit better, but the reason why is these red and green thrust and coast arcs are all right on top of each other. So there's sometimes you thrust, sometimes you don't. But all these right here are essentially on top of the asteroid's orbit, because we're changing it ever so slightly that you really can't see a difference in its orbit from a plot like this around the sun. But we're changing it so its arrival condition at the Earth is a little bit different, and we leave in June 2020 and arrive in June 2023 at the Earth. And so now I'm going to show you some crazy gymnastics in the Earth-Moon system. And this right here, these plots are in a rotating reference frame, which, even though these look all squirrely like scribbles of a 2-year-old, they're more understandable in a rotating frame. And in the video, you'll see it in the inertial reference frame. And it does make this in-game look like a bunny rabbit, which is kind of nice. But here in the rotating frame, what we can see is, you see my mouse? Can you see my mouse pointer?
Yeah.
Yeah.
So we come in interplanetary like this, and we do a lunar flyby here. And then we're swinging out around the Sun-Earth L2 Lagrange point. And we're using the sun's gravity to change our energy with respect to the moon. And then we do some thrusting, and we swing around the Sun-Earth Lagrange point again. And we're changing our energy with respect to the moon again. And so we come back for our second lunar flyby, we're much lower energy, and the moon then can capture us into this DRL. And so here you see this down here is us coming in on that second lunar flyby. And this is an Earth-Moon rotating frame. And we do this lunar flyby, and then we're here in this loose DRO. And we're kind of squiggly. And it's at this point, we're stable for about 2 years. If we turned it off, we'd be okay for about 2 years. And then eventually, we would probably escape into the Earth-Moon system and float around there. But by doing little bits of thrusting over and over again, we trim this orbit and we bring it tighter and tighter until we get to the screen orbit. You can kind of barely see under the blues. And the screen orbit here is still going to dance around a little bit and change, but it's going to be bounded. And it's going to stay there at least for several hundred years, probably for many millennia. It's going to stay there. So in this design, we spent about 35 meters per second to go to the end game. We expect that actually probably none of this delta V is needed. We probably can just use the sun's gravity to do all the work eventually as we do more homework and basically do more. The design process is basically similar to banging your head against a concrete wall. You just try lots of cases, and then after you get one that works, you then back out and figure out what caused it to work. And then you sound really smart when you explain, oh yeah, well you do this and this and this, and then it works. But it's really a lot of trial and error, and then like figuring it out after you've done it. And we're in that process right now of banging our head against the wall and trying a lot of different things. So in some of our runs we get ballistic captures, but we have to learn a bit more to understand what we are accidentally doing that's causing the ballistic captures so that we can move clearly. But I expect we'll have that probably down shortly. And then we'll sound really smart because we say, well, of course you do blah, 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 and you get there. Now this orbital trim maneuver thing, that's about 25 meters per second to stabilize the orbit. And so you see the in-game delta V is split up. Now, these delta V's might sound small, but remember, you're carrying a frickin' asteroid and it's heavy. So you want to go as low as you can. Let me go to the next slide. Here's the animation. So there's the Earth, and we've left the Earth. Blue is coasting, red is thrusting. And we're basically trying to catch up to the asteroid. We've dipped down, we're racing on to catch up to it. So we're coming up behind it, going to get it. This is inertial frame. Then we get to the asteroid. We're still getting, now we're there. And then we've got it in the bag. We have our captured asteroid. We're very close to the asteroid's orbit. We're just thrusting it a little bit at a time to redo the aim point as it is naturally coming up on the Earth. Red is thrusting, so we're going to start out thrusting early. And then we're going to start coasting pretty soon. And now we're really close to it, and we just need a little bit of few burns here and there to finally trim it up. And actually, in this case, the Earth is actually coming up on us, the way this asteroid encounters Earth. And so the Earth kind of races up to us, and we get there. And we do the flyby of the Earth, and now you'll see in the inertial frame this in-game orbit. It looks not just like a bunny rabbit, it looks like the bunny rabbit from the movie Donnie Darko, so it's kind of a menacing evil thing. And again, the inertial frame is kind of cool, but from a design point of view, you really need the rotating frame to figure out what's going on, because these just looks too complicated for it. We're going back down, the moon's going to capture us. Now this is what the DRO looks like in the inertial frame. It's an orbit around, it's actually a three-body orbit of the Earth and the moon at the same time. And so it's like zigzagging around the moon, and its motion is bounded to near the moon. Next slide here. I think I'm going. So, again, from an orbit point of view, that, if we have an Alice 5 class launcher, we can close the mission, but it requires a spiral trajectory, and that's going to require multiple eclipses and radiation belts, which makes system engineers unhappy. And it's better suited for target asteroids when you have more time. Heavy launch vehicles eliminate the spiral phase, and you can have later launch dates and a simpler spacecraft design. And we have these other asteroids that if we characterize, we can find out if they're retrievable. And but we are planning to design to new targets as they are discovered. And potentially with a spiral trajectory, you can even identify a target while you're spiraling out. We want it to be a cowboy about the whole thing and actually change your target after launch. And right now the DRO is our storage orbit, but there's definitely more research to do there. I'm going to try an adventure in video conferencing here. I'll show you another movie that I think of. It's not liking. Oh, there it goes. You see this movie?
Yeah, we see it.
All right. So this is, I want to show you what the DRO looks like. On the left, we have the inertial frame around the Earth, and on the right is the Earth-Moon rotating frame. So here's what the storage orbit looks like. So I'll just play it again. It's kind of squiggly in any reference frame, but it's bounded. So it will stay around the Earth-Moon system. Now let me go. Do you see me?
Yes.
So I don't know if I picked the right level for the talk. So it's I'm sorry if I was too complicated. It's easier to be complicated than be simple, especially because we're learning all this stuff right now, and it takes a bit of time to be able to explain it well and sound like a genius. So anyway, I will take your questions now. Just whatever you want to ask me.
All right, here we have one question. Thank you, Nathan. We have a question.
Just briefly, this thing is going to be
orbiting around the moon, does that mean we're going to be able to see it in 2026 or whatever from the Earth on a telescope? You're actually going to see it floating.
I can't hear the question, I'm sorry.
Sorry. In 2026, are we actually going to be able to point a Earth telescope and watch the asteroid float in front of the moon it's going to cross in front of the moon according to your trajectories, it looks like.
I'm sorry, I really can't hear the question.
He wanted to know, since the trajectory was going to be in the Earth-Moon system, will we be able to see it from the ground using a telescope?
Yes, except it's going to be moving through the sky fast, so it's going to be hard to point the telescope that quickly. I've done some only rough calculations of it, but I'm hoping that if we, if the asteroid's big enough and we paint the spacecraft bright enough, that maybe we can even potentially see it in a dark sky on Earth. But of course, then to do that, you have to get close, and that's kind of dangerous. So it would be a shame to crash just because you wanted to see it in the desert. But it's still cool to see it, right?
Yeah.
Thank you.
Another question?
Yeah, maybe I missed it, maybe I was just a little slow. How are you planning on destabilizing the asteroid in order to get the capture? What was the methodology to stop that rotation?
So what we do is, the asteroid is spinning. And if it's spinning around a principal axis, we can match its spin rate. But if it's tumbling, it's going to be trickier. We could potentially, basically, if it's tumbling and spinning, we could be flying with RCS thrusters, a kind of crazy trajectory, and come in that way. But that's not what we want to do.
Okay.
What we're going to do is match the spin rate so that if it's tumbling, it's just going to look like it's nodding, and the bag is flexible, so that as we get it on, then the bag is going to be nodding with it. And it's a mode that Brian Wilcox says, well, imagine when the dog catches the car. So as soon as we get there, it's going to have so much inertia than we are, so it's going to take us for a ride. And we are just going to give up and go for a ride. And so then that's one reason why we stitch down quickly. So that gets a nice connection quickly, so it takes us with it and reduces the amount of time that it's scuffing against the bag. But we get down onto the asteroid, and then what has happened, because we have this long extension, we've changed the inertial properties. And this is something we've only learned through simulations, but basically in the worst cases where it's tumbling, what that tends to do is put it into a flat spin. And so we just wait for it to go into that flat spin, and then we use the thrusters on the spacecraft to de-spin it. And the nice thing about the flat spin is it basically gives us a very long a moment arm to de-spin it. But in the other cases, when we don't go into flat spin, where it's a principal axis rotator, we just, after it calms down, then we just use the RCS system on the spacecraft to de-spin it. And that's really, that whole process there is the main thing that limits the size of the asteroids we can return. So the bag is a bag, and it can be scaled up. I don't know if you've seen, I guess I'm from California, and every house has termites, so we tent every house whenever it sells. And so there's pretty big tents for tenting a house, and so you can get a big bag, and you're really limited ultimately on the size of your bag. What limits you is the size of the bag you can test on the ground. But Glenn has this giant vacuum chamber, so we can test pretty big stuff. So that's the bag. That doesn't limit our size so much as the de-spin. And so the amount of fuel it takes to de-spin becomes a limit on the asteroid side. I mean, once we get cavalier about returning asteroids, we can imagine other systems where maybe we attach and then deploy a boom so that we're out and have a good moment arm to better de-spin. But that's the spinning.
Nathan, I noticed that when your bag went around it and you try to de-spin it, it's not twisting the bag as it's. You would think that it would be.
That's because it's a public outreach animation, and it was hard enough to.
Okay. The other thing that I thought you said that was very interesting was that you don't actually do a numerical optimization of the trajectories. You're taking shots at different trajectories in design space and then evaluating the results. Is that correct? Is that because
we actually do numerical optimization?
Okay.
But if you do in this system, there are a lot of local minima, and so the numerical optimization isn't good enough alone. you have to vary the input conditions to find the right trajectory.
So
the one I showed is an optimal trajectory. It's like using the most deluxe optimizer we have, but we can tweak the initial conditions and get another one with no thrusting.
Yeah.
And that's just the problem between local optima and global optima.
Okay.
And generally what happens is we do this a few times, and then we find out what works, and then we can backwards explain it to ourselves, and we're like, well, of course, this is what we should have done to begin with. But, eventually we'll learn how to do it, and we won't have to do this trial and error. We'll just say, well, yeah, using some freshman physics that don't occur to us right now, we'll say, well, obviously, this is how you set up the problem and optimize it down.
Or maybe we just take a citizen science approach and you give us the modeling capability and we let students around the world just have at it.
Well, yeah, I hope to this summer to start engaging the astrodynamics research community and basically give them enough information about the problem so they can start writing papers and tell me how I'm an idiot and I didn't think of something obvious.
Wait, we have another question.
How important is making a decision on which asteroid you're going to capture plays a part into your having a difficult time to figure out what orbits you're going to be using or what trajectories you're going to be using? Because you don't have a choice at this point, right?
Did you hear that,
Yeah.
David? I mean, Jonathan, did you hear that?
So you're asking, like, basically, how do we design orbits to the asteroid when we don't know what the target is?
You don't know what the target is at this point, yeah.
All right. So what we've done is there's a couple, there's about 30 asteroids that could be returned, if we could characterize them. So we can design trajectories for those. And then also we can take larger asteroids and design trajectories for those, because even though we can't return them, there's like I think 9,000 known asteroids, and so it gives us a good set of test cases to run. Now, as we do this, we're learning our techniques better and better and better, and our goal is eventually, so pretty much within an hour of when an asteroid is discovered, we will run the trajectories and get an answer back right away, before they even finish characterizing it. So in doing this, it looks like there might be a couple asteroids that will be characterized well enough by the end of the year, so we'll have those targets. But we want to keep looking because there's probably better stuff out there. I mean, we could get lucky. In 2009 BD could be, so what's gold in this asteroid mining business is a carbonaceous chondrite, because you can extract water from it. And water for in situ resource utilization is wonderful. But, we might not be so lucky in 2009 BD, might not be perfect. And even if it is perfect, things can happen and then we lose our launch window or whatever. So we're going to keep looking for targets and eventually develop a way so that we can just build the trajectories as they're discovered.
Any other questions? Yeah, one more question.
When you're referring to the spin rate, what is the magnitude on what you're expecting these asteroids to spin at?
Did you hear that,
right now,
Nathan?
Right now we're designing to a maximum spin rate of 2 RPM, which we think is pretty conservative. If you look at the models, there could be some crazy, you could have some crazy shard of metal spinning like really, really fast, though we think that's unlikely. Though if it's most likely we think it is like a rubble pile, it's probably spinning much more slowly.
Anything else? I think you've exhausted our class, Nathan. They've run out of questions, but I want to thank you for the presentation. And as you know, we're not going to make it public, until you tell us it's good to go. And if we have other questions, we'll circle back with you when you have a little bit more time.
Okay.
Thank you, Nathan.